Compact copper conductors represent an advancement in electrical wiring achieved by compressing standard stranded copper wires. This process increases the strand count while maintaining the same American wire gauge size, resulting in several advantages. Firstly, compact copper conductors exhibit a reduced cross-sectional area compared to their traditional stranded counterparts. This smaller size enables easier handling and installation, particularly in tight spaces where conduit field is a concern. Secondly, the increased strand count contributes to greater flexibility. This enhanced flexibility simplifies bending and routing of the wire, reducing the risk of damage during installation. Thirdly, compact copper conductors offer slightly lower electrical resistance due to the increased copper density. This translates to improved energy efficiency and reduced voltage drop, especially in long runs. The National Electrical Code, NEC, serves as the definitive standard for electrical installations in the United States. It provides comprehensive guidelines for conductor sizing, conduit fill, and other crucial aspects of electrical work. However, specific tables for compact copper conductors are not explicitly provided in the NEC. Therefore, determining the appropriate conduit size for these conductors requires a slightly different approach. To accurately size conduit for number 12 compact copper conductors, a step-by-step method is needed, incorporating the manufacturer's specifications and relevant NEC tables. Firstly, obtain the cross-sectional area of the number 12 compact copper conductor from the manufacturer's data sheet. This value, typically expressed in square millimeters, is essential for subsequent calculations. Secondly, consult the appropriate NEC table for conduit sizing based on the number of conductors and the type of conduit being used. These tables provide recommended conduit sizes for standard stranded copper conductors. Thirdly, calculate the ratio of the cross-sectional area of the compact copper conductor to that of a standard stranded copper conductor of the same American wire gauge size. For example, if the cross-sectional area of a number 12 compact copper conductor is 8.5 square millimeters and the cross-sectional area of a standard number 12 stranded copper conductor is 6.5 square millimeters, the ratio would be 8.5 divided by 6.5, resulting in approximately 1.31. Fourthly, multiply the conduit size obtained from the NEC table by the ratio calculated in the previous step. This adjustment factor accounts for the smaller size of the compact copper conductor, ensuring proper conduit fill. Continuing the example, if the NEC table specifies a 1-inch conduit for 5 number 12 stranded copper conductors, the adjusted conduit size for 5 number 12 compact copper conductors would be 1 inch multiplied by 1.31, resulting in 1.31 inches. Since conduit sizes are typically expressed in standard increments, select the next largest standard conduit size, which would be 1½ inches. Note that this calculation provides an estimate and that local electrical codes and regulations may have additional requirements that must be followed. Always prioritize safety and compliance when performing electrical work. In instances with multiple conductor sizes within the same conduit, calculations become more intricate, demanding precise adherence to NEC guidelines. Firstly, determine the total cross-sectional area of all conductors occupying the conduit. This necessitates summing the individual areas of each conductor type and size. Secondly, refer to the appropriate NEC table, specifically Table 1 in Chapter 9, which outlines the maximum allowable conduit fill based on the conduit type. Thirdly, calculate the percentage fill by dividing the total conductor area by the internal area of the selected conduit size. This percentage must remain below the maximum allowable fill percentage specified in the NEC table. Different conduit types, such as rigid metal conduit, RMC, electrical metallic tubing, EMT, and flexible metal conduit, FMC, possess varying internal diameters and fill limitations. Consequently, selecting the appropriate conduit type is paramount for ensuring code compliance. Factors influencing conduit type selection encompass environmental conditions, mechanical protection requirements, and the degree of flexibility needed for the installation. The NEC provides specific guidelines regarding conductor dating, which addresses the reduction in ampacity of conductors due to elevated temperatures or multiple conductors bundled together. When conductors are installed in close proximity, such as within a conduit, heat generated by the current flow can accumulate, raising the conductor temperature. To prevent overheating and potential insulation damage, the NEC mandates derating factors to be applied to the conductor's ampacity. These derating factors are based on the number of current-carrying conductors in the conduit and the ambient temperature. Derating calculations necessitate careful consideration of the conductor's insulation type, the ambient temperature, and the number of current-carrying conductors within the raceway. Failing to adequately derate conductors can lead to overheating, insulation failure, and potentially hazardous conditions. Grounding and bonding are fundamental aspects of electrical safety, ensuring a low-impedance path for fault currents to return to the source, thereby facilitating the operation of overcurrent protective devices. The NEC provides detailed requirements for grounding and bonding, covering topics such as grounding electrode systems, equipment grounding conductors, and bonding jumpers. Proper grounding and bonding practices minimize the risk of electrical shock, equipment damage, and fire hazards. Ensuring the integrity of grounding and bonding connections requires meticulous attention to detail, utilizing appropriate connectors, and adhering to torque specifications. Conduit fittings and connectors play a critical role in maintaining the mechanical integrity and electrical continuity of the conduit system. The NEC mandates the use of listed and labeled fittings and connectors that are suitable for the specific conduit type and application. These fittings must be properly installed and tightened to ensure a secure and reliable connection. Selecting the appropriate conduit fittings and connectors is essential for preventing moisture ingress, corrosion, and mechanical damage to the conductors. Furthermore, proper installation of these fittings ensures a continuous grounding path throughout the conduit system. Voltage drop refers to the reduction in voltage that occurs along a conductor due to its inherent resistance. Excessive voltage drop can negatively impact the performance of electrical equipment, causing reduced light output, motor overheating, and other operational issues. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. Voltage drop calculations involve considering the conductor length, conductor size, current flow, and conductor material. Selecting conductors with adequate ampacity and minimizing conductor length are effective strategies for mitigating voltage drop. The NEC provides guidelines for calculating voltage drop and selecting appropriate conductor sizes to meet the recommended limits. Overcurrent protection devices, such as circuit breakers and fuses, are essential safety components that protect electrical circuits from overloads and short circuits. These devices are designed to interrupt the flow of current when it exceeds a predetermined level, preventing damage to equipment and reducing the risk of fire. The NEC mandates the use of overcurrent protection devices with appropriate ratings for the specific circuit and application. Selecting the correct overcurrent protection device involves considering the conductor ampacity, the equipment's full load current, and any applicable motor starting currents. Regular inspection and testing of overcurrent protection devices are crucial for ensuring their proper operation and reliability. Working with electricity can be inherently dangerous, and it is essential to follow all safety precautions to minimize the risk of electrical shock, burns, and other injuries. Always de-energize circuits before working on them, and use appropriate personal protective equipment, PPE, such as insulated gloves and safety glasses. Follow lockout/tag-up procedures to prevent accidental energization of circuits during maintenance or repair work. Maintain a safe working distance from energized equipment, and be aware of potential hazards in the work environment. Adhering to these safety precautions can significantly reduce the risk of electrical accidents and injuries. The information provided herein is intended for general guidance only and should not be considered a substitute for professional advice. Electrical installation should always be performed by qualified and licensed electricians who are familiar with the NEC and local electrical codes. Consulting with a qualified electrician ensures that the installation is safe, compliant, and meets the specific requirements of the application. The NEC is a complex and comprehensive document, and interpreting its provisions requires specialized knowledge and experience. Relying on the expertise of a qualified electrician is essential for ensuring the safety and reliability of electrical systems.